Good afternoon, everybody.
Hello, good afternoon. Hello, friends. In our ongoing series of technical lectures, I welcome you all for the 12th lecture by NCTS. Today we have with us Mr. Rajesh Agarwal, and he will be appraising us on optimization of process parameters for HPDC. Mr. Rajesh Agarwal has over 30 years of experience in the field of product and tool design for aluminum die castings components in automotive and non-automotive sectors. While working in the industry, he was the recipient of Best Casting Award in ELICOS 2010 and NADCA 2011 International Die Casting Design Competition Award. Presently, he is based in Pune and providing consultancy, training and design services through his own venture, TechSense Engineering Services, to various OEMs, Tier 1 and Tier 2 die casting foundries. With this introduction, I hand over the session to Mr. Agarwal. Thank you. Over to you, sir.
Thank you so much, Mr. Soni, and thank you so much for the opportunity to enable me to present this session to all the participants. Good afternoon, everybody. Today we will be talking about the process parameters that are being used in the die casting process, and we will try to understand the correlations or the different way these parameters behave and work. So we'll have a few slides, just a brief introduction about TechSense Engineering Services, and then we will be talking about the various parameters used during the casting process, like cavity fill time, plunger diameter, plunger speed, gate area, gate speed, venting area, casting pressure. So today we will be focusing on all these variables to understand the various formulas and correlations and understand how do they be when they go into the shop floor for production. TechSense Engineering Services was founded in the year 2017 with the vision to simplify the engineering for die casting process and tooling. I have a strong belief that the die casting actually is a simple process, but with our varied experience by the different people and different foundries, we make it more complicated. And my way of thinking is, if we go with the engineering way, it is easy to understand and easy to understand the process as well as to execute the process. And to create experiences where passion and purpose come together to delight our customers. Our mission is to improve business productivity and profitability by value addition to TechSense as well as to all our customers. So at TechSense, we provide complete solutions for aluminum die casting, that including gravity, low pressure, as well as high pressure die casting. And our services are basically divided into 4 segments. The first one is a die casting process simulation, where we use the Magma simulation software to optimize the die casting process before the dies are really manufactured and put on the production. The second vertical is the die casting process optimization, where we work very closely with the various foundries on the shop floor to optimize their process as well as to reduce their rejections, cycle time, yield improvement, all those different areas we work with the shop floor on the process optimization. The third area is the design of the die casting dies. So we provide the complete solution from the product design till the complete die casting die design, including all 3D, 2D, bill of material, everything, and with a special emphasis on the thermal balancing of the dies. And of course, the fourth vertical is the training. So we provide training to various foundries, various Tier 1 OEM suppliers, various tool rooms, where we focus on bringing in the awareness about the engineering or the basic engineering behind the die casting process. The major focus is on that. So in the same line, we got in touch with the NCTS IIF, and Thank you very much for organizing this session, and we'll be talking about the basic fundamentals, the basic variables behind the die casting process. So as a die casting process, when the liquid metal is processed and due to various operating conditions, some defects are generated, which renders the part unusable. Sometimes these defects are in acceptable range, but the defect is always there. So if you see the middle portion, if you see that the casting process is where the defects are generated. So we can look at it in terms of the input process output. If the metal is as a basic input, the die casting process is where the liquid metal gets solidified. And then we have the secondary process where we have the fettling, short blasting, machining, painting, all other secondary process are being done on the aluminum casting part. So the defect generation, what we are more interested and more focused is during the die casting process, whereas you can say it's like a black box because that the change of the state from liquid to solid is happening in this during the process inside the die. And here we can safely assume that the metal preparation or the metal what is coming in is of good quality because metal preparation itself is a whole big subject which can also lead to various type of problems or issues. But our focus mainly will be on the die casting process. If we look at the various parameters used during the die casting process, on the metal side, we can say the metal composition and metal temperature. So which is very easy to control as well. It is easily accessible and visible to the user. On the machine side, we have a clamping force, the die clamping force, the plunger diameter, the metal injection speed, the casting pressure. And there are few more variables which are goes along with this variables which I have mentioned. The die side, we have the cavity fill time, the gate area, and the venting area. So these are the some of the key variables I will say. I will not say these are the only variables. These are the major variables which impact the die casting process in a big way. So we try to understand the correlations of these various variables or how do they interact with each other. Due to this process variation, various defects are generated inside the casting. NADCA is a North American Die Casting Association based in North America. So they identify the 22 types of defects in die casting, like surface defects, lamination, gas porosity, blister, flow porosity, shrink porosity, heat sink, leakers, cracks, inclusion, soldering, carbon or dye buildup, erosion, cavitation, outgassing, edge porosity, bending, warping, clash, excessive flux, stained casting, waves and lakes, cracks, deformation, and cold plates. Today, our focus is not on the defects. Today, our focus is to understand the key variables and how do they interact and how do they behave. Or what is the basic engineering behind these variables. So we will start with the basic die casting process. This I think all of you must be knowing. No, I don't need to explain this slide. As we go along, we'll come back to this slide again. So I have just a basic question. When the metal flows in the cavity, so what type of flow is it? Is it a laminar flow or is it atomized flow? We're talking about the high pressure die casting. So any answer I request you can type in the chat box. Any answers? What type of flow is it when we produce the casting using the high pressure die casting process? Any answers? Okay. When we talk about the high pressure die casting, it has to be atomized flow. And when we talk about the gravity and the low pressure, it is usually the laminar flow. right? So when we talk about the high pressure die casting, it is always laminar flow, and maybe in one of the subsequent sessions we will go to the details why we have to go for the laminar flow, or sorry, atomized flow for the high pressure die casting. So as the metal leaves the holding furnace, it continuously loses the heat. So whatever temperature it is there in the holding furnace, and once the metal start coming out with the ladle, it will keep on losing the heat continuously, right? So as the ladle goes to the near the machine, it pours the metal in the short sleeve, and then the metal flows in the short sleeve for the first phase, and then the filling happens. The temperature drop down rapidly. So this is a very short time, section of a second, where the filling happens, right? So as you see, the metal will continuously lose heat. It will not regain the heat until unless there is some additional or external heat input to the liquid metal. Since in the holding furnace, it is continuously heated to maintain or sustain a particular set temperature, right? So it retain the heat and stable at that holding temperature in the holding furnace. So it keeps on reducing the heat, losing the heat. Now, if we look at the solidification process, the heat transfer by conduction is dependent on geometry of the medium, the thickness of the heat transferring medium, the material of the medium, and the temperature difference. The rate of heat conduction through a plane layer is proportional to the temperature difference across the layer and the heat transfer area, but it is inversely proportional to the thickness of the layer, right? So as you can see over here, the rate of heat conduction is directly proportional to the area and temperature difference, inversely proportional to the thickness, right? So we can just try to understand if the thickness is less, right, the rate of heat conduction will be more, sorry, will be less. Am I wrong? Yes. If the thickness is less, the rate of heat conduction will be more. The rate of heat transfer will be more. If the temperature difference is more, also the rate of heat transfer is more. If the thickness is more, the rate of heat transfer will be less. Right? Now, if we try to emulate these conditions, what we're talking about in the basic aluminum as a basic die casting process, so we can assume aluminum thickness where we have a temperature on both the sides of the wall, and then we have a mold where we have a temperature outside of this mold thickness, right? And then we have a heat transfer from aluminum to the steel going out, right? That is why Q1 and Q2 is the heat transfer going out, right? And this is the casting thickness. So we can try to understand and visualize if the thickness is more, the rate of heat transfer will be slow. If the thickness is less, because the heat content also will be less, the rate of heat transfer will be much faster, right? And the heat transfer during metal filling as well as during solidification. As soon as the metal comes in contact with the steel, it starts losing heat. So we can simulate this basic understanding what I just mentioned. We can try to understand and see what happens in the simulation, right? So you can see we have a varied thickness cross sections. The more thickness and the less thickness. The less thickness, the rate of heat transfer will be more, and it will solidify very, very fast, right? On the other hand, the thick casting, the rate of heat transfer is not so much. It is not fully solidified yet. Right? So the basic question is the solidification process same during metal filling as well? The answer is yes. We have a similar solidification process during metal filling as well. So as soon as the metal comes in contact with the steel, it will start forming the cold layers. Now, we'll come to this, based on this basic understanding of the solidification behavior, we can calculate the fill time required to fill casting, right? As per NADCA, the following equation is used to calculate the fill time. Now, if you go through the formula, there we have some constants and some temperature values and some conversion factors, right? A is empirical derived constant. For aluminium, it is 0.0346 seconds per millimeter. Ti is the temperature of the molten metal as it enters the die. Tf is the minimum flow temperature of the metal. Td is the temperature of the die cavity surface just before injection. Means that is after the die is closed, after the spray. S is the percent solid fraction at the end of the filling. This is a variable which helps us to decide how much temperature drop we allow during the filling, or in other words, you can say how much solid fraction. Suppose there is 100 ml of liquid, how much percentage of solid we allow by the time the cavity is filled. Right? As we talked in the previous slide, during filling also the solidification behavior will be there, and metal will definitely be getting solidified during filling as well. Correct? So this percent metal fraction, solid metal fraction, is a very, very important variable. Right? We will go further detailing of this as well. So Z is a unit conversion factor. For aluminium, it is 4.8 to 5.9, and TH is the casting thickness. Now, when we talk about S, the percent solid metal fraction, S is lower for best surface finish, and S is higher for lower porosity. Right? So, if the casting, you have a critical castings where you need a very high surface finish, or you are doing some chrome plating or painting on the castings, then it is better to have lower value of S. So now you can see with the formula, if the S is lower, the fill time required also will be lower. If the S is higher, the fill time required also will be higher. Correct? So now when we talk about S is higher for lower porosity, means what? So that we are allowing more metal to solidify it by the end of the filling. Right? That is what we're trying to say with the S higher for lower porosity. So the chances of porosity will further reduce with that. Now coming back to this formula, we can put up this formula in Excel sheet as you see on the screen, and we can try to calculate the fill time required. Here we have two rows. The upper rows is like you can say the basic condition, and the second row you can say is basically comparison only, just to understand what is the impact or what is happening. Okay. Now, if I look at these variables with a casting thickness of 3 millimeter, right? Percentage solid of 25%, solid factor of 3.8, die temperature, flow temperature, and metal temperature. The estimated fill time required is 0.047. Now, keeping all other variables same, if I just reduce the die temperature, what is happening? the fill time required is less, right? The fill time required means the cavity should be filled in so much of time. Earlier, with this temperature, the cavity fill time required was 0.047 seconds. With the reduced high temperature, the requirement on the fill time increases, means I have to fill the cavity in a much shorter fill time. How much? We can see about 11.8% less fill time. Now, just as a comparison to understand, to achieve this less fill time, I will have to increase the speed of my plunger by 13%. We will come back to this point again in detail in the upcoming slides. Right? This is just for comparison purpose, what is the impact and what is happening. Now, if you recollect, we had a formula over here, temperature difference. If the temperature difference is more, right? Let me repeat, if the temperature difference is more, the rate of heat transfer, the heat conduction will be more. Means what? The temperature difference over here is more, the rate of heat transfer will be more, so the cavity fill time required will be less. So that is the interpretation. So that is the way we have to locate it. And as I just explained, the fill time requirement, right, is reduced by 11%, 11.8%, and the short speed required to be changed by about 13.3%. Now, we can simplify this formula by using a thumb rule, where we can say the fill time required is equal to K into TH. Now, if you go back to the formula over here, you can see there is only the major variable is the temperature and the thickness, right? So now if we try to put all these variables put together as a constant K, which can vary from 0.012 to 0.016 for different alloys, right? For the normal ADC12, it is normally 0.016. For some special structural alloys, ALSI 9, MNMG or silicon type of structural alloys, normally we consider 0.012. Where T is the maximum cavity fill time, TH is the casting thickness, and other variables we'll understand in the upcoming slides. Now that what we are trying to see in this slide, with this assumption of this thumb rule formula, we are trying to basically match this formula with the Nadka formula. So there is not much of difference. If you see the fill time as per Nadka software formula and the thumb rule formula, it is almost more or less on the same lines for the different casting thicknesses. Now, what we are trying to understand over here is that the cavity fill time is the most critical parameter in the gating design, right? As I just explained, it depends only on the casting thickness and temperature conditions. This also leads to the direct relation with the various cold defects. This will further elaborate in the upcoming session. Due to the machine performance, flow length, temperature drops, and other considerations, usually while we designing the die, we should consider 75 to 80% of the calculated fill time. Now you will be having a question, why don't we consider the safety factor in the initial condition stage itself, right? So that is actually depending on the understanding of the die casting process. Some people are really able to manage their foundry conditions so well that they don't need to go to this safety factor, what we are just talking. Consider 75 to 80% of the calculated fill time while designing the die. Means you still again considering a safety factor of 20 to 25% on the fill time, right? So it is variable for the different counties, for the different regions, different countries. So that's why NADCA suggests to be on the safer side, you consider this. If not feasible, you still consider 100% of the required fill time. Because many a time, this might be leading to over-designing. Over-designing means making it too robust, which may be not required. Correct? So that's why the fill time becomes the most critical parameter in the whole die casting process. Now we have the basic understanding of what the cavity fill time is. Now we try to understand how the cavity is being filled up, right? So now you can see we have the liquid metal volume, the plunger, right? The gate, the cavity ejection system, the injection system, the hydraulic cylinder on the injection side. All these are the various components. Now we'll understand these one by one in detail, just to see how they get correlated. Okay. As you remember, so far we have talked about the fill time. Are you not able to hear me, Mr. Soni? There was a message that someone is not able to hear. Is only Mr. Sushant Bhuyan or everybody not able to hear me? Mr. Soni, are you there?
Yes, sir. I'm available, sir.
Yes.
Even if he's not
Yeah,
available.
yeah. No, I'm there.
Some people, one person has messaged that he is not able to hear.
So it must be his audio problem. I'm
Yeah.
from Calcutta. The audio is okay.
Okay, fine. Thank you. Let's continue. So,
Yeah, please
as you
continue.
remember, so far we have discussed about the fill time requirement without having any volume. We talked only about the casting thickness, right? Now, when we talk about the dry casting process, so it is not only the fill time, we have to fill up a certain volume. So it is the component what we are designing the die for, the volume of that component, right? So now we are trying to convert here in this slide what you are seeing, we are trying to convert that fill time to the flow rate, right? Now, with the basic understanding of the fill time, rest of the calculations all will be based on the flow rate. So what we were talking about, what is the flow rate? The basic definition of the flow rate is a flow of the unit of the volume per unit of time, we can say, right? So what is the volume over here is the cavity volume. And if we talk about the die casting process, all our calculations and understanding is basically starting from the gate, right? So the volume after the gate. So the cavity volume, what I have mentioned over here is basically the cavity volume after the gate, means it will include if I have provided any overflows, chill vent, riser, or whatever I have provided after the gate. So that is the cavity volume. And this fill time required is basically coming from the previous calculation what we just saw. And that calculation is basically depending on the casting thickness, right? So depending on the casting thickness, we get this fill time required, and this is the cavity volume after the gate. So that's how we get Q1. I am just naming this flow rate as the Q1 and calling it as a flow rate required in metric cube per second. So my sincere request, if anybody is trying to use this formula, always remember the units has to be matched. If the units are not matching, you may end up in the completely, different figures or the different understanding. Now, how do we achieve this flow rate? So we achieve this flow rate by the fast short speed, the velocity, and the plunger cross section area. Right? The fast short speed is basically the V2, what we call on the machine, the second phase speed, and the area cross section area of the plunger. Right? That will be invariably giving us the plunger diameter. Correct? We can replace this AP with the pi d square by 4, where the d is the plunger diameter and Vp is the plunger speed, the second phase speed, again in metric cube per second. Now, the basic point over here is that the flow rate achieved, let me just go back to the previous slide. This is the plunger, right? That the plunger will be moving to fill this metal into the cavity, right? So that will be achieving a flow rate, that is a Q2. So Q2 has to be more than or equal to Q1. Q2 cannot be less than Q1, should not be less than Q1. Right? By equating these two formulas, cavity volume divided by the fill time equal to plunger speed and the plunger cross section area. The objective over here is to achieve the required flow rate in HPDC machine with the proposed plunger diameter and the fast short velocity. Right? Now, we can put up this basic formula, whatever I had mentioned so far, Q1, Q2, we can simply put this in the Excel sheet. Right? You remember we have considered the casting thickness. We can calculate the fill time required. Then we have the different weights, right? Then we have the weight after the gate. That will be the sum of casting weight plus overflow chill vent weight. That is the weight after gate. There we have a variable, that is the liquid metal density, converting these grams into volume. Then we have the volume after the gate and the metal flow rate required, that is Q1, right? So as you can see in the Excel sheet, I have maintained the flow rate as centimeter cube per second, right? Accordingly, all the units are defined, right? By missing the units, it's very, very difficult to manage. Now, when we go to the second part, the formula, you can see the short sleeve plunger diameter, right? The plunger area, that is the pi d square by 4, that is the d, pi d square by 4. Plunger fast short speed, right? Here you can see the green color cells or the blue color cells are the inputs, right? The plunger diameter is the input. The plunger fast short speed is also given as an input. And then we achieve certain flow rate and we achieve certain fill time, right? So what we are trying to say is Q1 more than equal to Q1? Answer is yes. Are we getting? So we can develop the simple spreadsheet because the formulas are no high-tech or no hi-fi formulas. These are a very, very basic, simple engineering formula. Right? Shall we go to the next part of it? So as we saw the process flow rate, one flow rate is coming the metal through the plunger and the second flow rate is at the metal at the gate. Right? So that's what we call as the Q3, the flow rate through the gate. Again, the flow rate is what? The cross section area into gate velocity. That is the flow rate. Right? Whatever the volume of the metal passed through that gate is the flow rate, and that is given over here as the gate cross section area, that is AG, and the gate velocity, that is VG. Again, metric cube per second. Similarly, we can say the Q2 should be equal to Q3. Right? We saw in the previous slide the Q2. the Q2 should be equal to Q3 means what? VP into AP should be equal to AG into VG. So what we are trying to look at this formula, knowing any three variables, please remember the word I am saying, any three variables, we can calculate the fourth variable. Are we getting? Right? So far we had 6 variables, right? So far we had 6 variables, casting thickness, fill time, that is the 2 variables. And then we have plunger speed, plunger area, gate speed, gate area. Total 6 variables so far. Again, we can say as a guideline, Q3 should be more than equal to Q2. Again, the objective is to achieve the designed gate speed. What do we mean by the designed gate speed? Usually, as per NATCA, the normal gate speed should be in the range of 25 to 40 meter per second. Right? To achieve this designed gate speed in HPDC machine with a proposed plunger diameter and fast shot velocity. Right? We can further see again the same thing we can see again in the Excel sheet. Right? Q2 we already had. Now we are calculating Q3. Right? So we are giving gate area as an input or metal speed at the gate as an output. Flow rate at the gate is also as an output. Right? Q3 has to be more than equal to Q2. Okay, then proceed. Now, you might be wondering why we are taking gate area as an input and the gate speed as an output. As I mentioned in the previous slide, you can take any variable as an input and you can change the formula accordingly. Right? So it is not necessary that you take the gate area only as an input or plunger speed as an input. You can decide. There is no limitation. But the basic formula remains the same, what we are doing over here. So based on this formula only, we are calculating these values. Now the fourth area is the ventilation. Let me go back to the previous slide over here. We're talking about the casting process. So when the metal is coming to the cavity, so what is inside the cavity before the metal comes in? The cavity inside is filled with the air, right? So whatever is the metal coming inside the cavity, whatever is the flow rate, the air also should be removed from the cavity with a similar flow rate. I hope you are able to get me. Whatever is the flow rate used to feed the metal to the cavity, right? The same flow rate should be used to remove the air from the cavity, right? Based on this understanding, we are calculating the venting area, right? What is the flow rate through the air vents? The vent area into the air speed, right? Here we are assuming the air speed in the range of 85 to 110 meter per second. The maximum air speed can be 210 meter per second. Beyond that, air will not be traveling. It will be like, what we call ultrasonic or different range it goes, right? So it will not be the normal air speed. Correct? So again, we can calculate the venting area with this equation. Now we have one more variable added over here, that is the venting area. The objective of this equation is to achieve the designed venting area in high pressure die casting machine with the proposed plunger diameter and the fast shot velocity. With the given Q2, I can calculate the venting area. Q4 should be more than equal to Q2. Right? So it is very, very important to make sure that the whatever is the air inside the cavity should be removed with the equal or higher flow rate. When we talk about vacuum, using the vacuum in the die, what we are doing, we are removing the air from the cavity at a much higher speed. That is what we are doing. So that is where the venting becomes very, very crucial and very, very critical. Right? If the venting is not enough, right, you can assume the formula. The Q2 is fixed from the plunger speed and the plunger cross-section area, right? And the venting is not enough. What will happen? The VA will increase, right? The speed of the air passing through the vents will increase. And if it is crossing 200 meters per second, it will eat away the die, it will erode the die. Right? So there are multiple issues, or the air may not go out at all. Air will get stuck inside the cavity, or it will be get entrapped inside the cavity. Right? So that is the importance of the venting. We can again correlate this with the same Excel sheet. We can put up these values. We can give the speed of the air through vents as an input, the ventilation area required as an output. Right? Now, there is one more thing what we had put up. Gas ventilation area, actually how much we have provided in the die. It is just an indication to understand, right? If you are providing 100%, your flow rate will be good, right? If you are not providing 100%, you can still achieve the same flow rate, but you may have to increase the speed of the air through vents. Are you getting how it is behaving? So these are the simple formulas put up in the Excel sheet, and you can have a very good understanding of these variables. You can play around this Excel sheet very easily by changing the different values, different variables, see what is happening and how it is behaving. Right? Now, there is one more important variable, that is the casting pressure. So what is the casting pressure? So you have an injection cylinder on the right side, that is the injection cylinder, and the plunger tip on the left side. Correct? The forces on both sides of the piston must be balanced, isn't it? So what we are saying over here, PHAH should be equal to PSAP. Right? What is PHAH? pH is the hydraulic system pressure, right? That is the pH, hydraulic pressure at the injection cylinder, and effective cross-section area of hydraulic piston. What is effective area? So it is pi by 4 ds square minus dr square. What is dr? Is basically the tail rod, correct? This is the simple mathematics. We calculate the effective cross-section area, the cylinder pistons d square minus tail rod d square into pi divided by 4, that is the AH, right? And hydraulic system pressure is the nominal pressure, what is put up with the in the phase 3 during intensification, right? What is PS? Is the static metal pressure. So that is the pressure which is applied on the liquid metal. So just in front of the plunger, we have the liquid metal. So the pressure applied on the liquid metal is the static metal pressure. And AP is again the plunger cross-section area, right? Based on the plunger diameter. So the formula is PHAH is equal to PSAP. So with this balancing, we can calculate the casting pressure being applied on the liquid metal. We can again put up the same thing in the Excel sheet, right? So we have a machine selected, and then we have a projected area, casting pressure. So how much clamping force required, correct? And based on the injection cylinder diameter, what is the minimum and the maximum intensification pressure setting, So what we are saying, the intensification pressure to be used to achieve this pressure is so much, right? You can put the calculation completely other way around. You can make the casting pressure as an output and the intensification pressure as an input, right? And these are the machine specific variables, right? The injection cylinder diameter, the pressure maximum and the minimum setting on the machine. And the projected area is basically to calculate the clamping force required. And this is the spare force ratio or the factor of safety. So requirement of the clamping force is 474 with this pressure, with this area, and the machine available is 560 ton. We still have a safety factor of 15.3%. So that is the basic understanding of the casting pressure. Are we getting? So these are the key variables which are used in the die casting process. Now, there is just a few questions or the understanding. How do we understand that? To overcome the various casting defects, the most used parameters on the shop floor are plunger speed and the casting pressure. The operator increases or decreases these variables as per his experience. But with the above understanding of these variables, we can easily optimize the process. Are we getting? If you talk to a foundry person or the supervisor or the operator, correct? You tell him that I am getting a known filling in a particular area. So what he will do? He will increase the speed or he will increase the pressure. Either one of them or both of them. Or maybe he tried different combinations for both these variables. Correct? Till he get a good casting quality in his hand. Right? So if you try to correlate the first slide, what we saw, the initial slide, this slide, I am talking about this slide. With the increase in the plunger speed, what we are doing? With the increase in the plunger speed, we are basically reducing the fill time. Are you able to understand what we are doing? Correct? With the reduced fill time, the plunger speed need to increase other way around. I mean, it is the same English understanding, but you can put in so many different words. Correct? To achieve a reduced fill time, you need to increase the speed. And if I increase the speed, I achieve a reduced fill time. What we are trying to do? With the reduced fill time, we are trying to compensate some of the variable, either here or here or here or here, anywhere. We are trying to compensate for some of the non-standard variable or the non-standard input. Correct? Non-standard input means, as we say, die temperature required is 200, but it is not 200. Then you have to compensate somewhere, right? How do you compensate? Increase the speed, reduce the fill time required, achieve a lower fill time. That is how you do. That is what I meant when I said we will see that in the later stage. That is what happens on the shop floor, right? Now, the second variable, increase the pressure. Now the cavity is filled. Now the cavity is filled, but you increase the pressure to pack the material, to push it more harder, right? Increase the pressure. So these are the most basic variables which are getting optimized or changed during the production process. Now, if you have gone through carefully the previous slides, if I am increasing the speed, B2, what will happen to this slide? What we are doing here? We are comparing Q4. We are comparing Q4 with Q2. If I'm increasing the plunger speed, that is the phase 2 speed, my flow rate will increase, means what? Q2 will increase. Since Q2 is increasing and it is more than Q1 is always okay, no issue. But as the Q2 increases, your Q4 also need to increase. Are you able to grab my point? As the Q2 increases, Q4 also must be more than Q2. Means what? Your requirement of venting area will also increase. Means what? You need more venting area with the same die. But what happens on the shop floor? Can you increase the venting area on the shop floor? No. The die is already manufactured and it is hanging on the machine. You cannot increase the venting area until unless you make the die loose and it will be flashing all around. But that is not expected, that is not desired, that is not the right way. Correct? So you cannot increase the venting area on the machine when the die is already there, but you are increasing the speed. You are increasing the flow rate achieved, right? But the venting is the same, so it will not be able to achieve the good ventilation. Means what? The sum of the air may still get entrapped inside the casting, which may again lead to some other defects. So when we talk about this condition, like to overcome the problem of non-filling or the cold shut, he is increasing the plunger speed, right? In other words, he is reducing the fill time, right? But in other words, he is also increasing the venting requirement, right? The venting requirement is also increased, and trust me, most of the time it is missed out. On the shop floor, we don't see that. Many times we have a perception that air will go away on its own, air will go out on its own, right? In that case is what happens if the air pressure is too much inside the cavity, it will lead to opening of the die and the flashing will happen. That is also one of the root cause for flashing, right? So these are the two important variables. Now let us try to understand one more thing, where we had compared Q2 and Q3, right? So that is just to understand the correlation, what is happening. If I am increasing the speed, as we just discussed, we are increasing the Q2, right? Since Q2 is more than Q1, no issue. But what happened over here? Q3 versus Q2. You need Q3 also more than Q2. But since the die is already made, it is hanging on the machine, right? The gate area is fixed, right? To achieve that flow rate or to make that same flow rate passing through the gate, what will happen? The speed of the gate will increase. Are you able to grab this point? How these are correlated? Just we said, we have only increased the plunger speed. Why the gate speed should increase? But there is a direct correlation. There is a direct correlation. Because the gate area is not changing when the die is on the machine, it is only increasing the gate speed. Because whatever flow rate you have achieved, the same flow rate will pass through the gate, right? So that is another very, very important correlation to understand what is happening over there. What happens to the gate speed, right? So any increase in the plunger speed directly affects the gate speed. But if these things are taken care during the initial design of the die casting die or the process design, then a lot of issues can be resolved beforehand. Lot of, I will say the number of trials or the lot of iterations can be reduced on the machine, right? So that is the basic understanding what we are trying to develop. And I hope you are able to get some insights into the basic engineering for the die casting variables, which are also part of the design variables. Right? Now, again, the important point, which I usually share during all my sessions, the integration of the product design, tool making, and the die casting as one team is very, very crucial to the success in die casting. If you miss out any of these variables, it will lead to failure. Right? You have product designer has made the product design with some intent, and it is not known to the tool designer, he will miss out something. Whatever you do, the casting will fail. Right? Tool designer has made something with some intention and is not fulfilled by the tool maker, again the casting will fail. Whatever you do here as a designer, as a tool maker, and if it is not executed properly in the foundry, it is again a failure. So that's why the integration is the key. Right? So with that, I come to an end of my session, and I thank you so much, Mr. Soni and the National Center for Technical Services, Institute of Indian Foundrymen, for the opportunity to share this knowledge with all of you.
Thank you, sir.
Thank you, sir.